Hey everyone, and welcome back. Today, we're diving deep into the science of aging. We all experience it, but what exactly is it? At its core, aging is a progressive decline in our bodies, driven by molecular and cellular damage that builds up over time. Our DNA gets damaged, protective caps on our chromosomes called telomeres get shorter, and our cells' energy factories, the mitochondria, become less efficient. This leads to the accumulation of damaged zombie cells that just sit in our tissues, causing inflammation and speeding up the whole process. But the good news is, scientists are now treating aging as a treatable condition, not an inevitable process. In this video, we'll explore some of the most exciting research initiatives happening right now, including drugs that eliminate those zombie cells, supplements that boost our cellular energy, and a groundbreaking TAME trial that aims to prove aging itself can be treated. Aging is an inevitable part of the human experience, yet it often evokes a complex mix of emotions, frequently dominated by a deep-seated fear and a powerful desire for eternal youth. This pursuit of staying young has become a widespread phenomenon, influencing everything from the products we buy to the way we view ourselves. We are surrounded by anti-aging products and treatments, all promising to reverse the effects of time and restore our vitality. This fascination with youth is fueled by societal pressure that often links youth with beauty and vitality, creating an unrealistic ideal that many feel compelled to live up to. The media plays a significant role, presenting images of eternally young celebrities and contributing to a sense that aging is something to be feared. This fear is not just about appearance, it also stems from a deeper existential fear of mortality and the desire for a longer, healthier life. Aging serves as a constant reminder of the limited time we have, which can be profoundly unsettling, and leads many to seek interventions to delay the process. Aging isn't just a measure of time, it's also a state of mind. Research shows that older adults often feel about 20% younger than their actual age. This self-perception isn't trivial. It's a powerful indicator of long-term health and well-being, often providing more insight than chronological age alone. One landmark study found that older individuals with a more positive view of aging lived an average of 7.5 years longer than those with a less positive view. This is thought to be a form of a self-fulfilling prophecy, where negative societal stereotypes about aging are internalized, leading to a less positive self-perception that can measurably shorten a person's lifespan. This suggests that our mindset can directly influence our biological aging, highlighting the importance of both psychological and physical interventions for promoting health and longevity. At its core, aging is a progressive decline, driven by a series of interconnected molecular and cellular dysfunctions. These breakdowns are known as the hallmarks of aging. These hallmarks form a complex web of cause and effect relationships. Understanding this network is crucial because it reveals that targeting one hallmark may have cascading effects on others, offering the potential for powerful, broad-spectrum interventions. The aging process is an accumulation of damage at the molecular and cellular levels. Our DNA is constantly being damaged, and while cells have repair mechanisms, they are not perfect. This leads to the buildup of unrepaired damage over time, which can increase the risk of tumor growth and drive cells into a state of decline. As we age, our bodies accumulate damaged, zombie-like cells called senescent cells. These cells have stopped dividing, which is a tumor-suppressing mechanism to prevent the replication of damaged DNA. However, these cells don't die off as they should. Instead, they linger in tissues and release a harmful mix of inflammatory molecules, which damages nearby healthy cells and accelerates the aging process. This accumulation of senescent cells is directly linked to many age-related diseases. This accumulation of senescent cells is often triggered by other aging processes. For example, telomeres, the protective caps at the ends of our chromosomes, shorten each time a cell divides. When a telomere becomes too short, the cell can become senescent. Similarly, the decline in our cell's powerhouses, the mitochondria, also triggers senescence. When these mitochondria become less efficient and produce harmful byproducts, it puts stress on the cell, causing it to become senescent. Senolytic therapies are a new class of drugs designed to solve this problem by selectively targeting and clearing these dysfunctional cells. The core idea is that by removing these senescent cells, we can reduce the inflammatory burden they cause and restore tissue function. In preclinical studies, a combination of senolytic compounds like dasatinib and quercetin has shown remarkable promise. Research in mice has demonstrated that clearing senescent cells can delay, prevent, or ease over 40 age-related diseases, including cancer and various heart, liver, kidney, and brain disorders, while also extending the animal's lifespan. Translating these successes to humans has proven complex. A small pilot study in patients with diabetic kidney disease confirmed that a 3-day course of dasatinib and quercetin successfully reduced senescent cell markers in their fat and skin tissues within 11 days. This provided proof that the drugs are effective at their intended target. The study showed that the treatment reduced cells expressing senescence markers. However, the functional benefits in humans are still being investigated. A Phase 2 trial funded by the National Institute on Aging looked at the senolytic combination's effect on bone health in postmenopausal women. The results showed no difference between the treated group and the control group in the primary outcome, which was a marker of bone degradation. The trial did observe a higher level of a bone formation marker at early time points, 2 and 4 weeks in the group that took the senolytic drugs, but this difference was not sustained by the end of the 20-week trial. These mixed results highlight a significant challenge in translating geroscience from promising animal models to human medicine. Our cells rely on a crucial molecule called nicotinamide, adenine dinucleotide, NAD+, to function properly. This molecule is essential for a wide range of cellular activities, from generating energy to repairing DNA. As we age, our NAD+ levels decline significantly. This is a major problem because many critical enzymes that are vital for cellular health and longevity, such as sirtuins and PARPs, depend on NAD+ to do their job. Without enough NAD+, these enzymes become less active, which in turn contributes to DNA damage, reduced mitochondrial function, and an increase in senescent cells. Researchers are trying to address this problem by replenishing the body's NAD+ supply. This is typically done through oral supplements known as NAD+ precursors, such as nicotinamide riboside and nicotinamide mononucleotide. These precursors are essentially the building blocks the body uses to make more NAD+. The goal is to restore NAD+ to more youthful levels, which would then reactivate the critical enzymes that depend on it, potentially improving overall cellular function. Human clinical trials have shown that supplementation with NMN and NR is safe and well tolerated, with most people experiencing only mild side effects. More importantly, these supplements have been proven to effectively increase NAD+ concentrations in the blood. Some studies have also reported promising functional benefits. For example, a study in middle-aged and older adults found that NMN improved physical performance, including walking endurance. One study even found that NMN supplementation nearly doubled the length of telomeres in blood cells within 90 days of treatment, a result that suggests a direct anti-aging effect at the molecular level. Despite these encouraging signs, a comprehensive review of the current research reveals that human trials have shown only modest benefits and are often limited by their short duration and small sample sizes. The definitive evidence for a direct anti-aging effect on human health span or lifespan is still lacking. A critical factor to consider is that NAD+ decline is caused not only by decreased production, but also by increased consumption by enzymes like CD38, whose activity is upregulated with age and inflammation. Simply boosting NAD+ with precursors addresses only one side of the equation, and may not be the most efficient long-term solution. A more sophisticated approach would involve a multi-targeted strategy that combines precursors with inhibitors of these NAD+ consuming enzymes. The current medical system is designed to treat one disease at a time. This approach is reactive and often begins only after a person has become sick. The core idea of geroscience is that instead of treating individual diseases like cancer, heart disease, and dementia as they arise, we should treat the underlying process that makes us vulnerable to all of them, aging itself. The biggest barrier to this is that regulatory bodies like the U.S. Food and Drug Administration, FDA, do not yet recognize aging as a treatable medical condition. Targeting aging with metformin. The TAME trial is one of the most significant efforts in this field today. It is designed to prove that aging is a treatable condition. The trial is testing metformin, a widely used and inexpensive diabetes drug that has shown protective effects against multiple age-related diseases and targets fundamental aging pathways. The TAME trial will recruit 3,000 adults aged 65 to 80 who do not have diabetes and will give them either metformin or a placebo for 4 years. The trial's primary goal is not to treat a single disease, but to see if the drug can delay the onset of a composite endpoint of major age-related diseases, including heart attack, stroke, cancer, and dementia. The trial is still in the active not recruiting phase as of its last update in May 2021. This means the study is ongoing and participants are receiving the intervention, but new participants are not currently being enrolled. The potential implications of the trial are enormous. If TAME is successful, it would compel the FDA to officially recognize aging as a treatable indication, providing a formal regulatory pathway for an entirely new class of longevity-focused drugs. The trial's design, which was shaped with input from the FDA, aims to create a template for a new regulatory pathway that would validate the geroscience hypothesis. A successful TAME trial could unlock immense investment in the field and fundamentally shift modern healthcare from a reactive, disease-specific model to a proactive, longevity-focused one. The 3 emerging interventions discussed, senolytics, NAD+ boosters, and the TAME trial, each represent a distinct but interconnected approach to combating aging at its molecular roots. The comparative analysis reveals that each approach has its strengths and limitations. Senolytics have a compelling, highly specific mechanism and strong preclinical evidence, but the human data to date has been mixed, highlighting the challenges of translating geroscience to humans. NAD+ boosters are proven safe and effective at a mechanistic level, but the observed functional benefits are modest, suggesting that simply boosting a single molecule may be insufficient without also addressing the underlying drivers of its decline. The TAME trial, while not yet conclusive, represents the most strategic and potentially transformative effort. Its value lies not only in the potential for metformin to extend healthspan, but also in its explicit design to create a formal regulatory pathway for aging as a treatable condition, a development that would unlock the entire field. The collective evidence presented in this video establishes a central argument. Aging is a malleable systemic process influenced by a complex interplay of psychological, genetic, and environmental factors. The most promising future interventions will likely be multi-targeted, addressing multiple hallmarks simultaneously. For example, a future therapy might combine an NAD+ precursor with a CD38 inhibitor to address both production and consumption, or it could combine a senolytic with a longevity-promoting lifestyle intervention. The ultimate goal of this research is not to extend life indefinitely, but to compress the period of age-related disease, frailty, and suffering into the shortest possible timeframe, thereby extending healthspan, the period of life spent in good health. The success of the TAME trial will be the critical catalyst for this new era, unlocking the potential for a medical revolution that promises to treat aging itself, paving the way for a more robust and vital future for all. Thank you for watching. If you found this information helpful, please hit the like button and subscribe to our channel for more deep dives into the science of longevity and health.